Okay. Hi, good morning, everyone. So last time we basically talked about the DCUPF, and we try modeled the DCUPF with the help of MATLAB, and we written a certain code as well. You can see here, this was the code written earlier that for a fiber system, how the LMPs are basically how we can solve the DCUPF and get the values of LMPs. Today, we will talk about different, basically like different type of formulation, or I would say different ways of solving it. So first of all, like if you simply, there is a tool in both MATLAB for MATLAB and Python, which is called MATPower for MATLAB and PyPower for Python. So this data is basically like available in that particular tool. And if you can see here, how, just a second. Okay, so if you see in this particular code, so it's basically like if you read everything, it's a 5 PGM fiber system, and here how to read this particular data. So you can see here, it's a base MVA is given basically 100 MVA. Then a certain bus data is given. So we are going to use this code here. Different attributes are given. So the first column represents the bus number. Okay. Then it represents the bus type. Okay, what is the type of the bus? So there are different buses like our PV bus, PQ bus, and Slack bus. So those information is available here with the 1, 2, and 3. And let me show you so here is the description of the entire file. So in the bus data format, the first column represents the bus number. Okay, then bus type. So they're like 1, 2, 3, and 4 is generally used, and we are basically like PQ bus is for bus like 1 is given, then PV bus it is 2, and for Slack bus it is given like 3 is the reference bus, and some isolated bus is there which is not connected. Then that particular bus will be mentioned with number 4. Then third is basically which is our interest for optimal power flow, real power demand, reactive power demand. So reactive power demand will come in ACOPF, not for the DC. Then some shunt capacitance, shunt susceptance, then some area number, like in which area that particular bus belongs, what is the voltage magnitude of the bus. So that is for power flow analysis, voltage angle. Then at 10 number it is given like what is the base kVA for that bus, like part of that the bus. So if there is some transformers, the base kVA will change in the entire network, so that is given. Then some loss zones are given. Then the important parameter like which we need for the OPF is maximum allowable voltage and minimum allowable voltage. So that is at column number 12 and 13. But for DCOPF, again, we don't need these columns as well, because we are assuming the voltages are 1 per unit only. Then the second data which is given is generator data. So the first is again like at what bus the generator is connected. Then this is like output of generator. So that is again for for different applications, but not for OPF, because we are like PG and QG is variable for the OPF. But 4 and 5 is basically important. What is the reactive power limit? So maximum and minimum limit is given, or the fourth and fifth column, that will be useful for ACOPF. Then voltage magnitude set points. What is the total base of this machine? So whatever the generator, what is the base for that? And we can put that machine either it in service or out of service. So this status will give you that. Okay. Then 9 and 10 is again important, like what is the maximum PG and what is the minimum PG, which is we are going to use for DCOPF as well. Then certain capacities and ramp rates are available. So those will be for when we are solving unit commitment down. So but for OPF we don't need this information for the time being, that to the extent which we are solving it. Then branch data is available here. The first column is gives the from bus number. So it is from which bus and to which bus. So it is basically 1 and 2 gives the connection matrix. Then third gives you the resistance of that branch, and fourth column gives you the reactance of that branch. Then charging susceptance shunt basically or for that particular branch. Then there are different line ratings available. Usually ride long term rating, short term rating, and emergency ratings are provided. And if it is equals to 0, then it is unlimited rating, and if certain values they were given, that will be the MVA rating of that particular line. Then some for a particular line, sometimes transformers are connected between two nodes. So what is the tap ratio of that? So that is given here. Earlier somebody asked me how to incorporate taps into the OPF. So yes, taps can also be incorporated. We will check about this as well. Then shift basically, like if a transformer is providing any shift, then what is the branch status, whether in service, out service, a minimum angle difference which a branch can allow, maximum angle difference a branch can allow. So this is the information available here. Then then generator post data information is given. So the first column gives you the like whether it is piecewise linear or quadratic, like polynomial. So polynomial is generally we like the, so far in our class we have used either linear or quadratic cost function. So then second is startup shutdown cost, third point. Fourth is like number of coefficients, and then 4 5 6 on. So it's like different parameters are given here. So the same information you can see in the like for case 5 which we are trying to solve. uh, so this is like PD and QD. Then base KVA maximum value is like 1.1 and 0.9 is the minimum voltage level which is allowed. Then for generator data, these are two generators are connected. Bus 1, then 3, 4, 5, there are three generators are connected. Then Pmax is 40, 170, 52, sorry, 520 and so on. So this information is given. Minimum is 0 is given. Then some R and X value is also given to us, and some line ratings are given, like 400 and 400 is the line rating. And then generator data coefficients are also given, whether it is like so there are three coefficients, which means we have A, B, and C. So this is like square term, this is linear term, and the zero is the constant term. Okay. Now this DCOPF program we have written here. It's like for DCOPF and using the LinPro. So we the cost coefficient which we have considered were basically like for two bus system we have written here. Okay, that no for our three bus system we have written this particular program. Now if I want to change it, and I will not write it with the help of LinPro. Let's write it for the uh, bus system. Okay, so first of all, what I will do is I will add this data. So data equals to, I think, load case and case 5. Okay, so if I do this and why there is an issue? attempt to execute script test as a function. Okay, so so if I run this one, the data is basically loaded on my system. So this 5 bus data is basically loaded on the our script. Now to perform DCOPF, we need certain entries basically. So if you see in this particular data, there are different information given. So first of all, I need how many number of nodes are there basically. Okay, so let me see how can we. So number of nodes basically can be calculated like nodes equals to so those nodes are basically length of the bus data. So like how many buses are there. So I will simply write down like length of dt dot bus data, and whatever is the length of the first column, that will give me the and number of nodes available in this particular. So okay, so we have, wait, this is case 5 bus. If you have any doubts, you can ask me. Okay, so number of nodes has been identified. Let's say a number of generators. So that will be generated data. Okay, so from the generated data, first column length can be basically given as a number of generators. Now let me define x. So what was x? So let me comment x. X was equals to basically uh, for a 5 bus system or for a 3 bus system or for any system. This is our formulation, right? So the if I go with the formulation, this is where my formulation is. So x, we have defined that p and theta will be the variables in this particular formulation. So okay, here if you see like p and theta will be the part of the formulation. So I will assume that theta 1, theta 2, theta 3, just for my reference, so that we don't get confused. And then we have generators p1, p2, p3, p4, and p5 are the generators with us. Now what we are doing to solve is basically, instead of linear programming, because I'm using this function, which is fmincon. Okay, so this is my function which we are trying to solve here, and there are basically different information provided in this one. So I will just go one by one. What are the different informations? Okay, so fmincon function required. So let's see the help file first of all. So that you can also learn what are the different input data available in this one and how we can solve it. So if I zoom, so fmincon function is used basically for to solve a non-linear multivariable optimization function. Okay, so it is to find the minimum of constant nonlinear function, and the generalized statement for a nonlinear function is given here, that minimization of fx such that there are some this cx is basically some nonlinear inequality constants. Okay, then ceq is again a nonlinear equality constant. Then these three we are already aware about. Okay, that these are basically inequality constants, linear equality constants. This is equality constants linear. Okay, and then these are the lower bounds and upper bounds. So these are the different basically uh, input and output are standard form of the nonlinear programming problem. But can we solve this same problem for our DCOPS? So yes, we can solve it, because this C and X are generalized one. So here you either you can give a linear equation, or also you can give the non-linear equation. So I'm going to use this one because we are going to learn how to write down the ACOPF program. So just to understand how fmincon works, so first we will write it down for a simpler program. Then we will move with the non-linear problem as well. So these are different syntax of this one. So the different outputs are like x out our optimal solution function value. Then we have exit flag output, and then some lambda gradient and Hessian is also can also be obtained as the output of this solution. The input is basically you have to provide the nonlinear function first of all, then some initial condition, that what is the initial condition. Then A and B are basically the linear inequality constants. Then further you can provide the linear inequality constants, further upper lower bound and upper bound. And then if you have no linear constants as well, you can provide them. Options are optional, like if you do not provide them, the by default values will be given. So like I have provided some options. So it's like how to provide options are basically like optims function. So this optim options is MATLAB predefined function where I'm providing some options like for fmincon make display of, that's it. So it's I'm just simply provided so that, and there are multiple like if you click on this particular button and press F1, you will see the entire L file, that what options are available to us and how we can set them. So different options are available, what are their default values, and how you can like number of iterations sometimes, and tolerance and everything can be. So like constant tolerance is 10 to power -6 default properties. You can increase or decrease as well these. Okay, and similarly different values are available with us, so you can change them if you want to. Otherwise you don't provide anything, it's a linear one. So I have written this fmincon, and whatever is the syntax we have written it here. So first of all I have to provide a function to it. Okay, what is my objective function? Then some initial condition, then a b a q b q l b u b. And if we have nonlinear constants, we can provide those nonlinear constants as well here. Okay, so this is how we are going to use it. So I have to provide a function. So to provide function, I'm going to need like how we can write down the function. So what was the our objective function first of all? So this is what we have defined our objective function. So this is our objective function, minimization of the total cost, and total cost was summation of all the generator cost. And the total cost was quadratic in the nature. So we will try to write it down. Now, as we are moving into functions, so just like C or C programming and everything, some input has to be provided to the function. So to calculate cost function, what we need, so like coefficient a b and c are going like we have to supply this particular function. So in the very the third line of this code, we have loaded the case, like case 5 has been loaded. Is it visible to everyone? like you can zoom in to that particular lines basically, because I don't know, some issue is there, so I'm not able to zoom this screen. Okay, so now thank you. So first of all, to define objective function, I need coefficients, and coefficients are basically provided. Like if I look at the case file, the coefficients are provided here in the generator cost mpc dot gen cost function. So gen cost function will provide me the coefficient. So I will simply, let's say, uh, supply this particular function. Let's supply this particular function, the x. Yes, so x is my variable, so I have to provide x as well, and along with that x I will provide the generator cost function. So this dt, in the dt I have stored the entire load, and dot gen cost will give the basically our entire. Okay, let me rename it, because the function name should be the same, otherwise it will call some other function. So if I so it's, let's say, function dc. Okay, so this is what the name I have given, and let me open it. So the name should be dc, and that should also be in our main file. So the function name I have given is function dc, and the input arguments were generator cost. So this is the function I have defined first of all. Okay, now how we can solve it? So it's a simple, like this is what we have written here, right? That summation of, this is the total cost function, summation of ci pi. So I will simply write it down like this only. So first of all, I will need number of generators. So I will further define ng equals to uh, length of, here I have obtained generator cost. So whatever is the generators and whatever is the length, that will be number of generators. Then I can provide summation. So summation equals to 4 I equals to 1 to ng, and then I have just entered, and let's say I have defined some total cost equals to initially some initialized with a zero cost. Then total cost will be equals to total cost plus, so we have to define the our function. So function was like ap square plus bp plus c. So this is what basically, like if I go with this particular data, this matrix is basically available with me. So just let me copy you so that we don't have to toggle all the time. Okay, switch between the screen. So I have placed it, let's say, here. So this is what uh, gen cost is. And now what is a? So this first fifth column represents a, sixth column represents b, and seventh column represents c. Okay, for if there are three coefficients are there. So you can make it more generalized. I'm assuming that only three coefficients are there. All the cost coefficients are uh, quadratic in the nature. So I'm going with the three, and I'm just writing down the code. So I need first of all generator cost of the very first generator. So that is ith generator, comma, where is a available? At fifth location. So this is a, then multiply with p square. But in x, where is the p? That is the thing. So I have assumed that I'm going to follow this particular notation. So let me copy this notation as well here. So we are going to follow this notation. So if you see, p is at 1, 2, 3, 4, 5, 6th place. So P1 is at 6th place, right? So I will put X and I can place a 6, then multiply X and 6. So this is AP square. Then we can do the same thing as similarly we can have BP. So this is control C, control V. B is available at the 6th location and X6 represents P1. Okay. So, but the issue is like, this plus, then I will put the complete, and this is my constant which is at the 7th location and also equals to 0. But this is how I can calculate, like, if I apply this for loop for the number of generators, I will get the cost function. Is it fine so far? This is how we can define the objective function. Is there any doubt? There should be some doubt because whatever I have written is not correct. Some issue is there with this particular code. So one thing is that if you look at this part, the function is going to return f, and we have not defined f. So I will put, like, after this for loop, f equals to the total cost. So this is what the total cost will go into the f function, and it will be returned to our main code where we are solving it. Another issue with this particular code is this x6 is fixed. So I don't want x6 to be fixed. X6 is basically keep on changing. Here P1 is basically equals to x6. Then it should go for P2, it should be equals to x7, and so on. Basically, we have to update the x as well, because for the first generator it is x6, but for second generator it won't be x6. It will be x6. Let's say I can make it like x plus 5i. So 5 plus I will do the thing like for I equals to 1, it will be x6. Then if I becomes 2, like second generator, then it will become x7. So that is what we have here, like P2 is x7. Then P3 is what? P3 is basically equals to x8. So for whenever this loop goes to I equals to 3, it will give you the 5 plus 3 equals to 8. So that is P3. So this is how we can write it down. Another way of doing it is so this is if I place 5 here. 5 is basically number of angles. This is what we have defined here, right? So in the second line, if you see, x is defined equals to theta, theta 1, theta 2. So if 5 bus system we are solving, then there will be 5 thetas. If it is 14 bus system, then 14 thetas will be there. So this 5 needs to be updated all the time. So instead of that, I can provide, let's say, node, because whatever is the number of node, that many thetas will come. So instead of uh, writing a fixed code for a particular system, we can make it generalized. So I can simply put number of nodes, and whatever is the number of nodes, that those many thetas will be there, and then number of generators are there. So it's node plus I. So now this piece of code is very much generalized, but I have to define nodes as well. So I have calculated nodes in very first main file. So I will take as a input from the main file. So I can do this thing here, in main file, let's provide node as well, which we have calculated here in the fifth line, right? And we have also calculated number of generators, so we can supply those as well. So let me supply number of generators here as well, number of generators. And in function I can get number of generators as well, and then I don't have to calculate this one, number of generators, so I can remove this particular part. Is this clear so far? So what we can do is we can delete this one, and this is the function which we have defined. So this is how you can define a function in MATLAB. Okay. So in games it was bit easier. Here you have to apply certain logic, then only you will be able to define the function. So let me save this particular file, and even I can get rid of this line as well, like f equals to tc. What I can do is, instead of tc, just simply use f. Okay. Or let's see, I'm going to use tc, and I will return that. Instead of f, I will return tc only. So this is my objective function file. Okay. Now let's go back to our formulation. This is our formulation, where second part is active power balance equation, and then we have uh, like limit. So this can be solved with the help of the lower bound or upper bound, and these two can also be solved with the lower bound and upper bound. And then we are going to need this equation. So there are two equations which we are going to put here. Now, so far objective function is done. I will come back to my main file. So I have defined this part in fmincon. The very first entry is objective function. So function is being defined. Now MATLAB understands that, okay, this is the function and this is what I have to optimize or minimize. Now I have to define x naught. So this is x which we have defined. So before defining x naught, I would like to define upper bound, that what is upper bound on the variables. Then I will define some x naught as well. Okay. And I will define the lower bound first of all. So like this is how I approach. You can do have certain different approaches. Now what is the upper bound? So upper bound is bound on the theta. What is the maximum angle it can have? So we already know about that. So it is how much? 3.14 pi we are using. So I will simply put 3.14 times, and how many times it is maximum? So it is like for 5 angles we have to define the upper bound. So I will put ones and 1 comma number of node. So again, it's instead of 5, we are using the node as a variable, so that if instead of case 5, if I'm going to solve it for 14 bus system, it will give me the same results. Then comma, I have to define the maximum limit of P1, P2, P3. So further I have values P1, P2, P3. So let's see where it is. So it is available in the generator data instead of post data, and in generator data at 9th column it is available. So I can simply put that value here. So I have that information in the generator data. So let's define it. P max equals to dt dot gen, and all rows comma 9th location will give me the maximum limit, and I will place it here, P max. Okay, so that is the maximum limit. Similarly, I can define the lower bound. So lower bounds are like minus pi and then P min. These are our bounds. You can also see, like, this is what we have written. Like on theta, it is pi by 2 or pi, and here again pi by 2 or pi basically we can use. So you can use pi by 2 as well. And then this limit like P max and P min has been defined. So we have defined all the limits on the variables. Now let me go back here. I have to define P min as well. So controls. This is P min. Okay. So this is the minimum value which we are going to need. So P min is at what location? 10th column. This is the 10th column. So let me see if I am doing it right or wrong. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10th column. Yes. So it is in 10th column. So we will use it. And instead of 9, I will put 10, and this is the maximum and minimum limits are defined. Now, can anybody tell me what will be the initial, or what should be the initial values for thetas? Please put your answer in chat box. What should be the initial value? So the maximum value for theta is pi, minimum value is minus pi for the angle. What should be the values for, like if I have to initialize it? So what should I keep? Yes. And Suman, what will be the initial value for this P? Uh, just a second. Yes, I'm sorry. I had to take that call. So yes, so P initial should also be 0. Thank you, Suman. So I will use that as a 0. So I will put zeros here. So it is like zeros, and it will be like 1 2 number of nodes, and comma zeros 1 2 number of generators. So this is what I have placed, right? Some error will be there if you are comfortable in the MATLAB. Many of you are. Can you tell me what will be the error in equation number 11 and equation number 13? Some error will be there. I have given you the hint that some error will be there in equation number, line number 11 and line number 12. So we will get some error here, and we will get some here as well. Can you identify that one? And I'm moving ahead. So in FMinCon, we have defined X naught. Okay. Now, should we define A and B equality constants? So what are the equality constants here? This power flow limits, right? So these are actually linear, but for this particular demo, I'm going to consider these as a non-linear constant. So I will not define those here. I will not define A and B. And similarly, this power balance equation is also a linear one, but I will define these equation as a non-linear as well. So I'm not going to use them. So I will put that my A is equals to a empty matrix, B is equals to also empty matrix, AEQ will be equals to empty matrix, and BEQ is also an empty matrix. So far we have defined up to this entire part. Now I have to define the non-linear constant. So let me open the non-linear constant. So this is, let's say, for DC. I have used it, and I will try to open this one. So this is a non-linear constraints for DC power flow, and this is, I will define here as well, DC. And we had power balance equation first of all. So power balance equation. So let me copy what symbols we have used. Okay, so I will copy these. Okay, here as well. That this is what X represents. So this is what X represents. Now, what is power balance equation? So let me define it. So how many times we have to we are going to write down the power balance equation? For all I set of node. So I have to apply a for loop just to write down the like if n is 5, so I have to write down 5 equations. So I will put n equals to 4. So let me go back here and I will use for I equals to 1 to nodes. But I have node defined node, so I will assume that I will get it from the main program because we have defined number of nodes there. Okay, so I will apply a for loop here. Now next part is what is the how we are writing the equation. So this is my equation. You can see it's a pg minus pd equals to pij. Okay, so I will try to write down the equation, and I assume that if you have any doubts, you can ask me. So first of all, I have to put the equation. So let's say it is equality C equality. So I will define C eq. Okay, and how many equality constants we have? First of all, I have to initialize. So it is basically let's say empty. So I have defined some CEQ, I have defined some C because these are the values which we are going to return. So I will define that CEQ 1, the first constant. So first constant is for let's say ith node will be equals to what value is there? PG minus PD. So PG is what? X, and PG's location is number of node plus I. This is the PG's location, right? And then minus PD. So PD is basically demand, and demand is available at bus data. So I will assume a bus data will also be provided me here. So I will put bus data, and for first node, whatever is the demand, so I will see that I will get this bus data. Okay, this is my bus data. So for first node, bus data is available at the PD is available at the third column. So I will put 3. This is my PG minus PD. That's it. Okay, so PG minus PD has been defined, and let's stop it here. Then I have to, if I go back here, so PG minus PD is defined equals to summation of Pij, and that is over j equals to 1 to n. So if I move everything on one side and make it equals to 0, this is how if you look at the standard form as well, like f min con. So CEQ equals to 0. So I have to make the entire equation equals to 0. So if I have to make entire equation equals to 0, what I can do is either I move all of these to this side or this to this particular side. So let's make it okay, this part equals to other side. So what I will do is I will, like, this particular equation, I will make it like summation of j equals to 1 to n, and this is pdi minus pi plus pij. This is what equals to 0. So this is what I will let's say want to make it. Then what I will do is I will change that here as well. So this is like pd minus pg. So I will put pd minus pg. Then I will apply again another for loop j equals to 1 to n, and in this particular loop we are going to basically add the pij. So I will again use ceq, and I equals to C equality constants, and I'm writing ith equation, and then I will add Pij. So Pi comma j we are going to use. So Pij was equals to theta I minus theta j upon xij. Is this correct? So Pij is theta I minus theta j upon xij. Yes or no? But the issue is I have to check whether there is a connection or not, first of all. So these are the branch data for which I can write down the Pij, not apart from that. So there is like, no connection between 1 and 3 in the branch data. So I have to only write down the equations for uh, following branch data. So what I can do is I have to identify the branches. So what we can do here is basically let's find out where is the branch I available. If there is a branch I only, I have to write down the code for that. So instead of writing this, I will let's use find function, find and find branch data. Okay, and in all columns, and then we have 1 and 2 equals to I. If I use it, what will I get? So first of all, let's see, try to solve it in the command prompt so that we able to identify that what this will give me. So it's basically and I value as well, like I equals to 1. So this gives me the number of rows at which this is available. And if I use 2, then it is 4th and 7. So if you look at this particular information here in the case 5, uh, 1 is connected at number 1, 2, and 3. 2 is connected at 4 and 1. Okay, so 2 is connected at 4 and 1, and what we have obtained here 5, 6, and 7 basically. So it is giving us the index, like the entire thing matrix is basically scattered, and the MATLAB made it as a vector and giving me 4 and 7 as a index. But I don't want 7 because there is no 7. So what we can change is basically obtain the from bus and to bus both. So what I will do is I will make it solve like this, and then solve at 2, and I will get 1. So we will use this concept and apply here that I am going to solve, let's say, from node, and that will be in the dt dot branch data, and that is in the very first column. Okay, then I will use 2 equals to find dt dot branch second column and I. Okay, so I have identified that ith bus is connected where. So what is the connection of ith bus? And let's supply the entire dt here. Okay, instead of we are going to need the dt, so I will supply that dt. So dt dot branch is available, and this information is available to me. Now, instead of applying for loop for all the number of nodes, what I can do is I just will apply the for loop uh, for the branches where ith bus is connected, because that is what I need. Other for others, it will be 0, right? So for I equals to 1 to length of let's say length of FR, like from bus. So if it is from bus, then how the code will look like? So this is like j equals to 1 to FR, and in FR we are getting basically the values like 1, 2, 3, 4, and 1. So like the branch number is coming to us. Okay, then if I use it, I can easily calculate Pij. Pij was nothing but theta I minus theta j. Okay, so theta I is nothing but xi always minus theta j. So what will be the value of the j? So we don't know like what is the branch number and what is placed in this one. So if I'm calculating from bus, so I'm identifying that ith bus, whichever is I. So for this particular case, I equals to 1. So this is I. So j will be 2, 4, and 5. So that will be available in this particular part. So I will place x dt dot branch, and then which branch we are looking at. So we are looking at fr jth branch. Okay, so this should be the branch, and then in this branch whatever is available at the second column should be the x. Did you understood this particular part or not? For the timing, like I can just to debug everything, we can copy this part as well, like control C, and I will create a temporary variable and I will put it here. Okay, so whatever is the it will be easier for us to debug. So this is our xi minus theta I minus theta j, and I have to divide the entire thing by xij, the reactance of the line. So reactance of the line is dt dot branch, and branch number was from j, and x is available at fourth column. So this is what I have placed like fourth column. So this is what it is basically. So I will copy this as well just to check whether we are getting the right x. X equals to let's note, make it x temporary equals to this part, just to verify whether we are doing it right or wrong. Okay, so this is I think enough xij, and so we have written it. Then I will apply a for loop, and similarly control C, control V, and this for loop is again for j times, but for two branches instead of one. That what are the two branches? Okay, and then I will calculate that for two branch, what is the temporary value of the other side. So it will be, instead of 2 it will become 1, and then again for two branch, fourth location will give me the reactance, and then similarly dt dot branch, here it will come two branch, and instead of 2 it will be 1, and then it is two branch, and instead of 4 it should be the 4 only. Okay, so is this correct so far? Okay, so as the time is going on, so let's assume this is what so C equality, anything else is missing in C equality. So if we go to the part, like we have written down this one and we have calculated Pij, so that is over. Then we will go to one theta reference we have to provide, that is also equality constant, right? So what I will do is I will put that as well here. Okay, so once everything is defined, so this is like C equality. What I will do is C eq and plus 1 equals to, and x equals to 0. So which x equals to 0 for the reference bus. So first of all I have to identify what is the reference bus. So let's say reference equals to I have dt dot bus, and I will put find dt dot bus, and in the entire bus type column should be equals to 3, right? So this should give me the reference, and if I like just to verify that for a 5 bus system, this should give me the 4, because at the fourth bus is our reference bus in this particular problem. So yes, this is my reference bus, so I will place it here, and I will use this reference as a fourth bus as a 0. Angle should be the 0. So theta of this particular reference should be 0. So this is I have placed x4 should be equals to 0. Why some error is coming here? Is this clear so far? Once we have done it, let me get rid of the code, which a lot of code I have placed. So yeah, fine. So this is it. Let's save it. And if I just one equation is still missing, which is the line, this basically line flow limits are still missing. So let's not go into that for the time being and try to solve it. So if I solve it, some error is coming, and I already explained you that some error will be there, and that error is because we are not basically doing this. So this p max is coming as a vertical, and we have to make it row. So I will place a transpose function here, and let's see if I'm able to solve it. Okay, some error is coming. Where? Line number 8. Reference equals to ref equals to. Okay, let's see whether this has some issues. Why there is error? Because we have solved it. Okay, I know. We have not supplied anything here. We have to supply these values. Okay, in man file, I have not supplied the DT, so this part was missing. Let's supply it and then run it. Okay, so lot of errors will come, and now this is like a node. Okay, so it's a typo error again. You should whenever I'm writing these equations, I make lot of mistake. It's typing error. So instead of I1, I have placed I. So that's why the error will definitely come. Let's run it. Still some error. Let's see. So undefined functional variable in this particular line. So we have not defined this bus. So let's put it dt dot bus. Again solve it. Okay. And let's see. So it has been solved, and let me see what we are getting. So let me see x, and let me see lambda dot eq. Okay, we can see it from the workspace as well. So this is what is our x values. So some thetas are coming. Then generator 1 is at 40, generator 2 is 170, then 362, 200, and 227. So we have obtained like P1, P2, P3 values here. Okay, and if I look at the lambda values again, so we can see those values here as well. So EQ non-linear one. So these are the equalities for non-linear equalities. Here we are getting 122, 212, 247, 342, and 55. So these are like for 5 equalities we are getting certain lambdas as well. So these will represent the LMPs for this particular function. Now I explained you earlier that everything here should be in per unit, but I did not assume, or I did not basically converted those values in per unit. So that's why the lambda which we are going to solve are basically different. So like what the result should look like is let me have a dt equals to load case, and I will put a case 5. So this is the dt, and let me make the limits 0 because we have not basically given any line flow limits. So but in this particular case 5, line flow limits are there. So if I just to see, those are at the branch level, and in branch line flow limits are given between 1, 2, 3, 4, 5, 6, 7 and 8. So I will use 6, 7 and 8 equals to 0. So branch all the columns, and 6, 7, 8 should be equals to 0. Okay. So I have updated this one, and let's say run OPF and DT. So let's see if some we are getting the same result or different. So these are okay. We are solving DCOPF. Wait. So let me put DCOPF and solve it. So we are getting some result here. So like generator 1, generator 2, generator 3, and some generation is there. Lambda is 118, and our lambda was something else. It was not 118. So and it was different as well. And this P1, P2, P3 are also different for our case. So if you convert everything into per unit, then you will not see these issues, because that if you look at the like again, okay, let me run again uh, this file which we have created so far. So this is like very fundamental one. So okay, why some error is coming now? Let me run it, and let's see the lambdas. So how so okay, this values we are getting optimal function is also fine, but if you look at the lambdas, the like upper bound and lower bound, by looking at these lambdas, like upper bound is like p1, p2, p3, we are getting certain lambdas. Similarly, this non-linearity, it is different, and this defies the concept which we have understood so far, that we have not considered any losses, we have not provided any transmission constants, but still the lambdas are coming different. But we understood that okay, lambdas should come equal if there is no losses and there is no uh, congestion, but it is coming different. So just to like I'm just about to end the session right now, but we will discuss this in the afternoon session why it is coming. Let me tell you, if like I will share this code right away in the canvas, you can go through it and try to correct it. And the correction is the where like we have to convert everything into per unit first of all. So if you are able to convert everything into per unit, you will see the different result. Okay. So if you have doubts, like it's already 11, so if you have doubts, we can have one or two quick questions. Okay. Otherwise, we will resume at 2. And in the meanwhile, you can go through these like 3 files I will share. These 3 are basically 4 files, and you can see whether it is working or not. And one more thing, yes. While running this code, you will not be able to run this command load case. Okay, because it is specific like met power command. So instead of using load case, you can basically copy these and change the name mpc to dt. That's it. So like, you can copy all of these matrices which is available in case 5. So I will share this case 5 and you can paste this particular location. And instead of MPC here, like, it is written MPC dot version MPC dot bus. Just use DT because this is what we have used in our rest of program. So you can just use DT, then you will be able to run this particular code. So that's it from my side. Thank you very much. Okay, we will resume at 2.